Yeah, let's get started. So before we actually continue with the section, just want to see if you have any questions or comments so far. Okay, just some logistics. First of all, so far you have submitted homework 1, homework 2, and I'm targeting on to try to grade them by end of this week. If not, should be by the mid of next week, so that you can get some feedback regarding homework 1, homework 2, and then we can go from there. And homework 3 is due by this Sunday. And note that homework 3 actually captures two. Hold on, I'm not sure which screen you can see. Oh, I didn't share my screen yet. Okay. Okay, now you can see it. Okay. Note that homework 3 actually covers 2 chapters, chapter 3 and chapter 4. You only need to pick 3 of all these assigned problems. No, actually for office hours, it should be alternate weeks. I'm not sure if you actually tried to log in last week. I was late actually. I kind of forgot it, but last week I missed it. So starting from next week, I shall be around at 8 p.m. on Wednesdays. And then I usually would stay around 15 minutes if no other students. If you want to make it, if you have any questions, please join me at 8 p.m. Alternate Wednesdays. Okay, so let's continue with chapter week 3 contents. Aaron was also asking, is it 3 from chapter 3 and 3 from chapter 4? No, it's just 3 overall. It's just for homework 3. Homework 3 actually covers both chapter 3 and chapter 4. Okay, there's another question regarding the meetup. Meetup is Wednesdays. I think probably the logistics in the admin side, they made some sort of mistake, but it should be on Wednesdays, and it's on the odd weeks. So this is the 3rd week of the semester. We have a meetup, and then on even weeks, it's this odd and even is just a general rule of thumb, but reality is because of the spring break, etc., it changed a little bit towards the end of the semester. But overall, odd weeks, 1st week, 3rd week, 5th week would be the regular meetup, and then starting from and 2nd week, 4th week, 6th week on Wednesdays 8 p.m. would be the office hours for this class. Okay, so no other questions, so we can just continue with the actual contents for week 3 and chapter 3 and chapter 4. So in terms of the presentation for chapter 3, the reason that for this section there are 2 chapters instead of 1 is mainly because chapter 3 is more conceptual. It's just trying to explain some of the basic fundamental ideas that you should probably have to keep in mind when you try to fit a model. And then when you're trying to analyze a collection of data points, you need to do 3 things. Number 1 is fitting a selected model type or types to the data. Precise meaning of the best model must be identified. So in this case, fitting a selected model type or types of the data. So you want to understand, you want to select which type of the model you want to, which type of methodology, which methodology you actually want to try. That's number one. The second task would be choosing the most appropriate model for competing types that have been fitted. So in this case, you have to find a criteria that is appropriate to evaluate your models. And then the third task that actually involves making predictions from the selected data. A criteria must be established for determining how to make predictions. So that's in general 3 steps, 3 major tasks for model fitting. And then when you we all know that we have some sort of data collection process and then data analysis process and making conclusion and trying to do prediction. And then sources of error could include formulation error. Formulation error essentially saying that the methodology that you picked may not fit the data itself. So that's one type of error. And second type is truncation error. This is more because of the precision of the type of analysis that you're actually trying may not fit the precision of the data itself. In that case, it might have this truncation error. And also runoff error, it's very similar to the truncation. Truncation probably more talking about the data truncation, but the runoff error is more the precision of the data. And then measurement error. Measurement error is trying to gauge how good the data collection process is. And then we know sometimes we could use visual fitting, trying to eyeball the relationship. It could be a linear relationship. It could be second degree polynomial, third degree polynomial, and then, but the reality is visual fitting has potential pitfalls. And then we all also know that when you study the I606, there's potential that you have when you trying to fit the model itself, you also have the potential of overfitting problem. So in certain cases, you have to do data transformation in order to identify the correct relationship. Majority of times, what happens, the reason that we really need data transformation is trying to transform a nonlinear relationship to a linear relationship so that it can be easier to be fit. And then Chebyshev approximation criteria. We can take a look at the figure 3.12 and follow-up example. Hold on, it's they have a new version and then it's much more difficult to navigate. Okay, now it looks like can't do this. So in this example, the basic idea was that you want to measure the line segments of AB, BC, and AC. Not sure if you guys can see it. Hold on. Okay. Represented in the figure 3.12, right? And then what you really want to do here is suppose that the measurement yield estimate AB is 13, BC is 7, and AC is 19. You see that AB plus BC is 20 instead of AC being 19, right? And then, as you should expect in any physical measuring process, this discrepancy results. In this situation, the value of AB and BC add up to 20 rather than the estimate of AC equal to 19. And then question is how to resolve the discrepancy of one unit using the Chebyshev criteria. And then we can use some sort of linear equations to represent that. And then let x1 represent the true value of the length of AB, and x2 is a true value for BC. So in that case, R1, R2, R3 represent the discrepancy between the true and measured value, so that x1 minus R1 is 13. In other words, x1 minus 13 equal to R1, etc. In this case, we will see that numbers R1, R2, and R3 are called residuals. And then if we really want to minimize the largest of the three, R1, R2, and R3. In other words, we want to use some sort of math model to be more intelligently to understand what's the measurement error, what's the correct residual R1, R2, and R3. And then we're trying to minimize the largest of the three numbers, R1 absolute value, R2 absolute value, and R3 absolute value. So suppose that if we call the largest number is R, then it's minimize R subject to the three conditions. The three conditions being R1 absolute value less than or equal to R, because R is the largest measured residual, right? So, and also R2 absolute value less than or equal to R, and corresponding R3 absolute value less than or equal to R. So that's a minimization problem that we come up with. And then each of these conditions can be replaced by the two equalities. For example, R1 absolute value less than or equal to R can be replaced by R minus R1 larger than or equal to 0 and R plus R1 larger than or equal to 0. And then we can use the math relationship that we found earlier between R and x1. We can reset the constraints, rewrite the constraint being to the following 6 constraints. And then I just want to mention that this is really a trick that we made. This how can we try to transform that absolute value to linear constraints. This is some sort of tricks that we can use in many of the linear programming formulations. So for example, even though here only threw out some of the ideas. For example, if we see that in some cases we can see that only one of the three independent, one of the three choices can be chosen. In that case, we can model it as three binary variables, being that x1 is either 0 or 1, x2 is a 0 or 1, and x3 is a 0 or 1. And in that case, if we set up a constraint to say that x1 plus x2 plus x3 equal to 1, that essentially tells us that only one of those three can be chosen. So in some of the models, for example, location problems in Amazon, Amazon location, any of the retail e-commerce sites or any of the um, um, supermarket that they need to consider some sort of location from warehousing, right? They need to find out the location of the warehouse. And then you can say that all the customers' demand have to be satisfied. In this case, we can use this type of binary tricks to represent the relationship that which customer demand will be covered by a specific warehouse. Just throw out some of the examples, some ideas to use that. This is one of them that shows here. So in this case, we minimize R and then with this constraint. Now it's a linear program. We are going to discuss more on the linear program in the chapter 6, even though apparently here it says that this particular function can be solved. And then if you're interested in how to solve this problem, you can go jump start to chapter 6, week 6 material. There is an example that I provided there, tells you how you can solve it. I believe one of the homework problem that was asking about how to formulate use Chebyshev inequality and then ask you to solve it as well. You can try to solve it using simplex using R code, not using the manual way to solve it. So in this case, you could use that as a reference. Apparently, if you cannot solve it, it's okay even for the homework problem. If you have the right formulation, it's already a good thing. It's great, great progress there. Okay. And then here it says, but this is pretty much the major idea of this problem. I just have some. I just want to give you a flavor of how we transform a specific problem to a linear program problem. Okay. And then in the chapter specifically, there's some other sort of criteria that we can use. For example, minimizing sum of the absolute deviation. This is one of them in the example. And also least squares criteria. And then just want to point out that this least square itself is the fundamentals for linear regression. We are actually going to cover a little bit here as well, very shortly, I believe. It happened that Neil was asking, in regression, we minimize based on the absolute value of the largest residual. It's really not Chebyshev method. What we're trying to, in regression, we minimize based on sum square of the error, which is which is exactly is the equation that I just showed. Hold on. This one. We are trying to minimize the actual value, the difference between the function value and the actual value squared, sum of that squared. That's how what it is. So that's sum of squares of the error is the minimization problem for linear regression. Okay, looks like there's another question here. Okay. Sekha also mentioned that LP solve of R is working great to solve the problem. That's correct, which is in week 6 material as well, if you want to use as a reference. And Mauricio has this question. Respect to the two least square equations in page 122, let's say 122. 3.6 and 3.7. Looks like we're using different reference. I have this 3.5 and 6. Ah, okay. 3.5 and 6. You are asking value when intercept and is not 0. This is really the intercept. B is the intercept. A is the slope. So it's valid in general. So either A could be 0, B could be 0, but this can be calculated that way. Because if you actually read this section already, we have that objective function being, as I said, it's objective function is really trying to minimization of the actual value minus the function value squared, sum of all of them up. And then in order to solve this, you need to take the first order derivative and then the second order, first order derivative and set them to 0. You can solve for A and B. So it's universal. So you can solve it for the slope and the intercept. And then apparently in order to make sure that it's a minimization, you need to take the second order derivative, and you can check that it would be always be less than or equal to 0, so that it's always be larger than or equal to 0, so that it's a minimization problem there. I mean, you can get the minimum that way. And then for you're talking about 3.7, let's say 3.7 is different because here is a first of all 3.5 and 6 is just really linear equation, right? Y equal to ax plus b in this case. Y equal to ax plus b is a linear relationship between x and y. And then but the next example here says y equal to a times x powered by n. You are right in the sense that b equal to 0. That's correct. And then, but this particular function form is totally different, right? It's a power curve. And then in this case, the book actually derived that a equal to this function form. 3.7 is only valid when the intercept is 0. That's correct. and its function form is y equal to a times x powered by n. It 3.8. So Honey was asking, should you do a log transformation? Its transformation is really depends. It's not straightforward to say that which type of transformation you should be doing. Actually, I believe the textbook has some example to see the order. There's certain function form that you can try first. And then for a function like y equal to a times x powered by 3/2, it actually falls into this power curve in some regards, right? So you could solve it just by this method, exactly on this page. And following up on that question, how does this Chebyshev criteria fit into regression or fit into what? Neil was asking about this question. Here you see what we're trying to minimize the number of max yi minus this function, right? But regression, we're trying to minimize some square of that square. So it's different. It's just different ways to think about what type of, in other words, in certain problems, it fits better to use Chebyshev approximation criteria. In certain other problems like regression, probably use the regression itself is better. So it's just different methodology here, essentially. Okay, that's great. So let's continue with yes, here actually on this page we just briefly went through the example, and also I just want to point out that least square criteria is sum of squares of the error. It's the foundation of the linear regression. And then in order to fit a straight line introduction to linear regression, you want to formulate the least squares, just as what we just saw there, and take partial derivatives, set partial derivatives to 0, solve for the slope and intercept. We went through 3.5 and 3.6 examples just now, and then those two, A and B, are the slope and intercept. And then fitting a power curve is really an introduction to nonlinear regression that we saw there. And then you can see that we also used taking partial derivative to solve this problem. But the reality is, there's many ways to solve a nonlinear equation. One of them is taking this partial derivatives. Later in the semester, we will be able to touch upon some other methods. For example, Lagrangian multiplier approach to solve the nonlinear objective function type of problem. And then transformed least square fit transformation from nonlinear to linear. The book has some discussion there as well. Hopefully, you can, when you come to that point, please read and ask questions if you have any. Yes, Mohammed was asking about, are we going to, in simpler method, are we going to cover duality? Yes, we are going to cover that, even though it's very fundamental. And how can we tell which program, dual or initial, is easier to solve? I think it's something that it's probably not a question that I can answer at this point of time. We can discuss a little bit further when we come to the chapter 6, and also when everybody is on the same page, we can talk about primal and dual and which one is easier to solve. Sometimes it's easy to detect which one is easier to solve. Sometimes it's not quite straightforward. And then regarding choosing a best model, as we know, there's a fitting error, so you have to compare different models in the sense that how to compare different models. The major considerations would be the error itself, complexity of the model, overfitting of the model, generalization of the model. Apparently, number 3 and number 4 are related. We don't want to be overfitting the model. We don't want to overfitting the data so that generalization is easier to be achieved. And then complexity of the model itself is also a consideration, just simply because that in some regards, we prefer that if we could solve the problem mathematically, we know we model it mathematically and we solve it, then we prefer this way rather than simulation, because simulation itself, we know it has some assumptions here and there, and it has some randomness built in. But apparently, if the mathematical model becoming too complex, we really want to go to the simulation route. Last session, we discussed the different methodology, including simulation in terms of complexity, in terms of computation time, in terms of the intuitiveness of the results. So that actually gives some perspective there as well. But in general, these are the considerations when we need to choose the best model. And then Param was asking, in the real world, do you see simulation being used more than the mathematical approach? I would say no, because it really depends. For complex systems, for example, in some of the economic what should I say? For example, for mathematics, if you use just the simple demand and supply, you can try to figure out the equilibrium in the economy. But if you have all sorts of input, including not only supply and demand, but also some physical policy from the government and many other uncertainties that you have to build into the system in order to predict the outcome of the system, such as interest rate. In that case, you probably really want to use a simulation. And then it doesn't mean that it's really just a pure simulation model, because you have some underlying pieces on components itself are mathematical models, right? So it really depends on the specific scenario. You can use a mix of both on each individual approach instead of it's hard to say which approach you actually which specific approach might work better. It's very hard to say. Okay, let's continue. These are the homework for this section, and for chapter 3. And then for chapter 4, we discuss an introduction, and then there are actually some examples for chapter 3, for the approach that I discussed earlier. And then this picture specifically give you some example that for data A, if the model assumption leads to the expectation of a quadratic model, then you use a parabola will fit the data as in B. And then also a smooth curve will work, which will be the C. And then apparently we start questioning whether there's overfitting for C, right, in this particular case. Okay, earlier you were asking how transformation. In this case, this is a lattice of powers, saying that this you want to try power first and then try itself. So essentially meaning that these are the sequence you might want to try for some of the transformations if you really want to test it. And then the book also shows for this specific example, book also shows for different transformation what the model look like. And then there's a Lagrangian form of the polynomial, which is saying that if x0 all the way to xn are n plus one distinct points and y0, yn are corresponding observations at these points, then there exists a unique polynomial px at most degree n with the property that yk equal to pxk. This polynomial is given by px equal to y0 L0x plus all the way to yn lnx, where lkx can be defined this way. So this is a Lagrangian form of the polynomial. It's worth reading the book for this example. And then again, there are potential problems of high order polynomials. The error might be smaller, but the complexity model is higher. And then potentially it can overfit the model and has less generalization of the model, right? So you have to consider all the 4 dimensions when you try to select a specific model. Sometimes maybe a linear model would just be sufficient. So in this case, I also already discussed that for polynomials, error can be worse. And then complexity maybe can be decreased, overfitting can be decreased, generalization of the model can be increased if we use a lower order of polynomial. And then cubic spline models. So one thing is on the chart on the left, it's a piecewise linear function. So this is some approach that we always use in many of the real world problems. You try to, instead of fitting the whole piece, for all the data, you're trying to fit different pieces separately, just because they might have different function form. In other words, if you look at scatter points, in many of the times, after you think about removing some of the outliers, in many of the times, by looking at the scatter point itself, already can tell you something to test. And then cubic splines on the right, which is S1x is a1 plus b1x plus a1x squared plus b1x cubed. And then read the examples in the textbook regarding this. These are the homeworks for chapter 4. And then, as I mentioned just now, homework 3 include chapter 3 and chapter 4, so that you only need to pick 3 out of this list. You don't need to pick more than 3. So you can pick 2 in chapter 3, maybe 1 in chapter 4, or the other way around. But please pick at least 1 in each chapter if you can. That's for chapter 3. Because that's for week 3, because we're not meeting next week, so we have to we should cover this as well. Before I continue, any other questions so far? Okay. So chapter 5 in this textbook actually talks about simulation modeling. And then I'm not sure if some of you already taken a simulation class. If not, you probably will take it next semester. And then here, simulation model in this chapter really just serve as an introduction to simulation so that you can get a perspective on what is simulation and then how it can be used, why, in what scenario it might be used. And then the textbook discussed simulating deterministic behavior area under a curve, and then also discussed generating random numbers and simulating probabilistic behavior, and with inventory model and queuing models, followed by the homework. So first of all, the rationale for using simulation models. When we are not able to construct an analytic model adequately explaining the behavior observed. So as I mentioned earlier, if we could solve it analytically, not too complex mathematics there, I would argue that if the model becomes too complicated, then it may not worth the effort to solve it analytically. So in that case, you probably want to use simulation. And then in some other cases, you can use simulation to obtain data needed for further analysis. So what happens is, for example, if you want to test a math model, you want to see whether your model actually works, but you don't know but you don't really want to test on some specific data, or you don't have the luxury to get that data yet. In that case, you can use simulation to simulate that data. For example, you simulate a normally distributed arrival of the traffic into a random intersection. In that case, you want to study how long the green light should be, how long the red light should be, etc. In that case, you probably can use some sort of simulation data. And then at the end, you can sample, right? You can go to some specific intersections to do some observation, and then to fit the arrival process into certain distribution, and then use that distribution to simulate a set of data to be used to do further analysis. And then in some other cases, maybe other than simulation, you just don't have any other choices. You have to use simulation just because of the deficiency of the data, deficiency of the modeling capability in certain regards. In other words, we probably don't know a lot in some cases, so that you have to make certain assumptions there. And then here says, so the behavior and versus model. So the behavior could be deterministic, could be probabilistic, and model can be deterministic or probabilistic as well. Let's take a look at this example, simulating deterministic behavior area under a curve. So we see that on the right-hand side, you can see that area under curve divided by area of the triangle can be approximated as number of points counted below curve divided by total number of random points. Suppose that it's x and y axis, right? We can generate two random number x and y so that you know the position of the point, and then using that position, you can determine whether it's under the curve or above the curve or in the square, and then you can count the number of points counted below the curve divided by the total number of random points so that you can get the area under the curve. So the input is total number of n of the random points to be generated in the simulation, and the output is the area, approximation area under the specified curve, y equal to fx over the given interval x larger than equal to 8, less than equal to b, where fx less than equals 0 less than m. So following the question that one of you discussed earlier, so suppose that this function itself is a quadratic function. We all know we will be able to solve the problem to find the area under that curve, right? But if this function form is not well specified, then other than simulation, we have no other choice. That's a perfect example in which case we want to use simulation. Okay, the steps actually included here is you need a counter equal to 0, really trying to count how many points that we generated. And then for 1 all the way to n, do step 3 to 5, calculate random coordinates. Step 3 is calculate random coordinates xi and yi that satisfies this relationship. And then step 4 is calculate fxi for the random xi coordinates. If yi less than or equal to fxi, then increment the counter by 1. Otherwise, leave counter as is, trying to count how many points actually are under the curve. And then calculate area m times b minus a times counter divided by n would be the area itself. And then you can output the area. In this example, I think there's a homework problem that was asking you to calculate the pi using simulation. So the idea is very similar. If you have a square and then you have inscribed circle, and then we can use simulation to get what percentage would be in a circle of all the points, and then correspondingly we can use the ratio between the circle and the square to get the relationship, and then you can find the percentage, and then you can approximately calculate the pi. This is, to be honest, I think in many of the cases when people are getting some sort of interviews, if they claim that there's no simulation, how to calculate pi is one of the examples that many of the interviewers might ask. And then volume under curve is very similar. It's the difference is only that volume under curve is number of points counted below surface in first octant divided by total number of points. So it's an extension from 2D to 3D. And generating random numbers. And this particular approach is called middle square method. You start with a 4-digit number x0 called the seed, and square it to obtain an 8-digit number, adding a leading 0 if necessary, and then take the middle 4 digits as the next random number. So this is one approach. And then there's another example. Another way to generate a random number is called linear congruence approach. That is to say that next random number equals to the previous random number times a plus b modulus of c, where c is the modulus, a is the multiplier, and b is the increment. Just pay attention to possibility of cycling and lack of statistic independence among the members in the list of random numbers. So in other words, if the one thing is cycle length, right? You can generate a random number if you really trying to simulate a complex system. If your random number is not long enough, that could potentially cause some sort of issues. And why I'm saying that, because apparently the choice of A, B, and C determines how quickly you might have met a cycle. So that's the second method we discussed, and the book actually has more detailed discussion about this, but I'm trying to point out to you so that you are aware of that. And then, okay, here is yeah, I missed the equation here, but in general, for the probabilistic model, there are three simple probabilistic models. One is the flip of fair coin, and second one is the roll of a fair die, and the third one is the roll of a unfair die or pair of unfair dice. So let's look at a fair coin. So we know that if it's a fair coin, what's the probability that in 30 draws, what's the probability that, we know it's should be 0.5, right? If it's a fair, and then the probability that you can get ahead is 15 out of 30. And then instead of doing that, instead of using it mathematically, so how can we simulate that behavior? The input is total number n of random flips of a fair coin to be generated in a simulation, and output is the probability of getting ahead when we flip a fair coin. And then in this case, similarly, we can just initialize the counter, and then for each step, you do step 3 and 4, you obtain a random number xi between 0 and 1, and then step 4 would be check whether it's between 0 and 0.5. If it is, we increment the counter. Otherwise, you don't increment the counter, and then step 5 is calculate p head equal to counter divided by n, output the probability of the heads p head, right? So this is a relatively simple example, and then apparently you can code this in R so that you can do the simulation. And then a fair dice, and then you want to count the percentage of probability for each row equal to 1, 2, 3, 4, 5, 6, and then you can correspondingly at the bottom of the page you can see that you can, in certain situations, you can try to increment counter 1 or counter 2 all the way to counter 6. So at the end you can use counter 1, counter 2, counter all the way to the counter 6 divided by n, so that you can get the probability of rolling being 1, 2, 3, 4, 5, or 6. And then what if it's unfair die? And then you can, and then we know, for example, in this case, counter 3 has a range between 0.2 to 0.4, which is 0.2 difference. And counter 4 actually between 0.4 and 0.7, which is 0.3 difference. So it's really not a fair die. In that case, you can do very similar approach as the previous approach, except that when you flip that coin, when you get that random number, you want to check where it belongs to, and correspondingly you can increment that counter 1 all the way to counter 6. And then note that apparently those three different probabilistic behaviors, we have some corresponding homework corresponding to this particular one. By the way, I really want you guys to read the book. It's more interesting to read the book itself than working through the problems. I mean, homework. What I really want to say is, finishing the homework is one thing, but trying to learn all aspects of it is rather more important than finish the homework. If you read those 2 chapters, what you have learned probably much more than you just pick 3 problems and trying to figure out the solution, and then you submit the homework, you got 100 points out of 100. That doesn't help as much if you read not as much if you read the textbook. So I'm saying that if you read the textbook, you probably learn much more. That's that. Let's continue. The textbook has 2 examples after this section. One is the inventory model, And then inventory model is one of the many problems that's facing a lot of the different stores, either supermarket or e-commerce companies. So, and then it's a function of the average daily cost is a function of storage cost and delivery cost and demand rate. And then assumptions on demand levels and frequencies of the demand level have to be made. Note that some of the assumptions for simulation models may be results from analytical models. This is actually I pointed out earlier already. And then for the inventory algorithm, input would be a queue, would be I think that's I couldn't remember exactly what that is. It's probably replenish quantity and time interval t and d demand, and s and but in general, this actually lays out the inventory model, and if you read it, you would get much better deep understanding of what it means. I read it a while back, so couldn't exactly remember what's key points here. And then for the queuing system, I want to say that it's a hardware system here. It talks about the queuing models. I provided a link in week 4 material talk about queuing models. And then in the discussion session, I also discussed some of the possible examples of queuing models. For example, I mentioned in the last class, in a supermarket in Target, you can model the service queue being arrival process of the customer being person process, and you can model the service time for the single server being the exponential time of service, and then you can use MM1 queue to analyze the behavior of the checkout counter. In other words, you can analyze time in the system, time with in the queue, time with the customer, time with the checkout process, etc. And then you can understand how the whole system works. But when it turns out that if a customer after 5 minutes of waiting, he decided to go to the next queue, then in that case, analytical models might be very difficult to solve it. So in that case, you can try to use simulation model to say that maybe each individual server is following an MM1 system. On the other end, customer behavior of changing lines or decided to pick up something else before he comes back again, then you can use simulation to analyze the whole system. It would be much more accurate in that regard. So review the lecture, review the stochastic process that some of the links that are shared in week 4. Now I think they are very helpful there. And then queue models can be used to analyze morning rush hour, can be analyze multiple server queues. I also discussed this already, can be used in supermarkets to estimate how many servers checkout booths might be needed as well. And then these are the homework for chapter 5. You only need to pick 3 out of this for next week. That's pretty much everything that I plan to cover for this meetup. So you have any other questions? I actually want to point out one other thing, that is the discussion board. The discussion board, I mentioned that you need to submit one post, but what I really want is not that you just submit. I actually want to see more interaction, meaning that I want you to read others' posts if you can provide some insights and we can all discuss something together. Of course, it's fine that you open a new thread to continue there as well, but really what I'm trying to encourage here is the interaction between all of you, learning from others. Know that someone saw something more interesting that you have never seen, some either some site or some project that other people have done, etc. So it's not to say that it's not fine that you whatever you do here now that you open a new thread. What I just want to emphasize is hopefully you guys can interact more there in the discussion board as well. That's everything from my end. Do you have any other questions? If not, we can just stop here, and next week, Wednesday at 8 p.m., I will be hosting office hours if you have any questions. Also, feel free to send me an email. Yeah, bye-bye. Good night.